And he is actually right now, he's the director of IREAP, which if those of you who know anything about IREAP, it sits in 2 colleges. So he has all the issues, the joys and frustrations that we have in 1 college in 2 colleges. So, but he comes from a postdoc, I guess, at JPL some years ago. 4 years, is that about right? 4 or 5 years?
I mean, you're very forgiving. It was, I don't know, 2009.
Oh, well, okay.
I wish it was 4 years.
Okay. Many years ago. Well, we met about 4 or 5 years ago. So, and he's spent times at CNRS in France, but he has 2 PhDs. One in what he calls nonlinear dynamics from his home in Cameroon, and then another one from Spain in what do we call that? In photonics, I guess, right? And so he comes wearing 2 different hats, and he's going to talk to us today on quantum microcombs. So, Yanne, put this right here on your.
Sure. Okay, so thank you very much, Wendell, for the invitation. Thank you.
I should mention, he does not have a schedule because he's local, but you can find him anytime. So if you want to see him, just come see him.
Exactly, very classical particle. So you can have my position and velocity. It's perfectly okay. So thank you very much, Wendell, for the invitation. Thank you very much for everybody attending, and for the people on Zoom. As Wendell said, my name is Yanne Chembo, and today I'm going to talk about quantum microcombs. When Wendell invited me, he was like, okay, I was like, okay, JQI. So of course, when we talk about microcombs, there are many aspects of it, but today I'm going to focus on mainly the quantum aspects of these objects. So just a few words about my lab. So I am at the head of the lab that I call the Lab for Aerospace and Communication Engineering. Most of what I do is geared towards aerospace and communication engineering. I am in ECE, so Electrical and Computer Engineering, and I'm also, as you say, the director of IREAP, which is the Institute for Research in Electronic and Applied Physics. It is an institute that sits in between CMNS and engineering, and that also overlooks 2 centers. The Nano Center is under IREAP, and the Quantum Technology Center. So I work on aerospace engineering, mostly microwave photonics, how to generate ultra-stable microwaves for aerospace applications. Photonic machine learning, trying to use the huge bandwidth provided by lasers for ultra-fast computing. Telecommunication engineering, of course, as soon as you work on lasers, one of the straightforward applications is telecom. And finally, nonlinear and quantum photonics, and this is what I'm going to talk about mainly today. And these are the results that I'm going to present. In part are those of the people in my group. They're all smiling, so I assume that they're happy and that they're satisfied with the results that we get. But what I'm going to present is in part due to their very, very hard work. So this is the outline of the talk. I'm going to introduce very briefly the concept of frequency combs. I know that many here are familiar with that, but there's a quote from I think it's Enrico Fermi that I like a lot. Never underestimate the pedagogic utility of repeating to people things that they already know. I'm going to talk about WGM resonators, whispering gallium mode resonators, and then we're going to talk about quantum microcombs and then conclude. So frequency combs. First, of course, we need to have a good notion of what a comb is. We are all very familiar with this concept here of a vibrating string. And of course, here we have like the mode n equal 1, n equal 2, 4, 5, etc. And basically, we have a resonance condition here that says that the length of the string you need to have in half integer number of wavelengths, right? But actually, the better condition is actually this one that says that in the round trip, you have actually an integer number of wavelengths. This is actually the one that is physically meaningful. And when you do that, of course, this condition here, what it translates actually, once you use this very straightforward High-School relationship, it translates basically to the fact that the eigenfrequencies here are discrete. So basically, the frequencies are an integer number of this delta omega 0. So it means that if we go to the Fourier domain, you will have basically a comb. You'll have a set of frequencies that will have these spacing here that is going to be constant, right? So basically here you have an acoustic frequency comb. Most of the instruments like the guitar, violin, will generate an acoustic frequency comb. And basically, if you replace the mechanical oscillator by an optical oscillator, so if instead of having frequencies of a few kilohertz, you are willing to go tens of gigahertz, terahertz, then you obtain an optical frequency comb. That's in a nutshell what's happening. So basically, optical frequency combs are sets of extremely narrow and equidistant spectral lines in the UV, visible, and IR spectral ranges. Something that is very, very interesting, and I always encourage my grad students when they start on the topic is to do this little mathematical exercise, is very interestingly, if you have here a train of what we call Dirac peaks in time, so you have infinitely narrow pulses, perfectly equidistant, that are flowing through time, duck, 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 so a perfect train of Dirac peaks. Well, when you do the Fourier transform, you obtain an optical frequency comb. And of course, when you have an optical frequency comb, if you do the inverse Fourier transform, you obtain a train of perfectly infinitely narrow temporal peaks, right? And this is why originally optical frequency combs were generated using femtosecond lasers. So basically, people were using the narrowest pulses that they could have at the time, and having a train of such pulses will translate in the frequency domain into an optical frequency comb, right? So this here shows the intimate relationship between having narrow pulses in the time domain and having a frequency comb in the spectral domains. So it might look like it's something that is rather trivial, but this is actually a Nobel Prize winning technology. And these two esteemed colleagues here, John Hall, Theodor Hensch, they got the prize for, and I quote, their contribution to the development of laser-based precision spectroscopy, including the optical frequency comb technique. And basically, the main idea here, knowing, for example, that John Hall was at NIST, is that if you remember, the relationship between optical frequency comb and the perfect clock is that when you have a very good optical frequency comb, then actually you can translate that in the time domain with a very, very accurate clock, right? And for obvious reasons, NIST is very interested into this type of technology. Good. And very important to stress here, both of them were working with mode-locked lasers. So now we are going to talk about WGM resonators and how do they fit into this big picture. So it's a very strange name. So when you start to work on this topic, you're like whispering gallium resonators, like, you know, this is quite a weird expression. It comes from the fact that if you go to the St. Paul's Cathedral in London, there is this dome. So this is when you're below, but if you're above, like the dome is like this, the diameter is like 32 meters. And if you're standing here and you whisper, someone that is exactly on the opposite side will actually hear what you're saying. And this is something that has been known. It was seen as, like, you know, just a curiosity, like a touristic curiosity. Actually, I have a good friend and colleague that was visiting London, and it was like, okay, you know what, I'm going to make the experiment. The thing is that, of course, it's there, and it's like tens of tourists, and all of them, of course, are trying to make the very same experiment. So you have a huge destructive interference, and nobody hears nothing, and they say it doesn't work. But if you have enough, I don't know, the clearance to vacate the place and to make the experiment, for sure it will work. The first one that actually described exactly what happens here is Lord Rayleigh. In 1877, he wrote a book, A Theory of Sound, where it was like, you know, it's actually obvious. It's just, you just have sound that is bouncing around the walls here. And this is how you can be on one side and hear someone speaking on the other side. So you can do actually the very same thing with light. So consider here that you have a perfectly spherical optical cavity. Yes, it's very. I try to make it as yes. So it's kind of like transparent. I try to have a marble, okay, with PowerPoint. So and now you have like a fidelity, for example, for photon injection. And if you are able to shoot a photon inside that cavity, what's going to happen is that by total internal reflection, that photon is going to be trapped, right? So it's exactly the same thing. And if you have another optical fiber tip, you can actually retrieve that photon. And here you see a picture. This is from, I think it's from the Valhalla group, where they basically use here an optical fiber. They melt the tip. And of course, when you melt it, it becomes a liquid, and then you have surface tension. It becomes like a microsphere. And you can see here that, like, you have these whispering gallery modes here on the equator, right? And here you have a microsphere that has a diameter of like 70 microns. 70 microns, that's typically the thickness of your hair. Twice as much, I would say. Yeah. So it works very well, and this is something that has been known for a very long time. So now, something that here I would like to call your attention to is that because the light propagates in the equator, actually you don't need the top part, you don't need the bottom part, and actually you don't even need the middle, okay? So you can have a disk, it will work as well, or you can have actually a ring resonator, it will work as well. So here, for example, you have an image of some of the resonators that I was using in my lab when I was still in CNRS in France. So here, this is a
question before we go on.
Sorry, come again, please.
Yeah, could I ask a question on the previous slide?
Yeah, sure, please go ahead.
Okay, so sure enough, you could make a disk, and that's what you're going to talk about next. But what breaks the symmetry that makes the mode be that particular equator?
Oh, okay, that's a good question. Actually, it will depend on where you basically inject the light. If here you have a perfect sphere, you can take any equator and it will work as well.
So, looking at the picture, is the thing that's sticking out the bottom, is that where the injection is?
Oh, no, sorry. This is so here, this the thing here at the bottom is the stem. So basically, this is an optical fiber, and they basically melted the tip of it. And because they melted so they heated it and it became liquid, and now you have basically surface tension that creates a sphere, and then
Sure.
it solidifies as a sphere. So the light here, it's not shown, but the injection has to be in the plane of this equator.
Okay, got it. Thanks.
No problem. Sorry, the picture is not clear enough from that perspective. So here you can see much more clearly that when we have here now a disk, so these are millimeter-sized disks. So they basically have the size of the button of your shirt. And here you have a laser that is hidden in the dark here, and here optical fiber, of course. And here we can couple, so the light comes this way, and here, of course, it's trapped here. Some of it goes out. So now, something that is very interesting about this picture is that this actually is a very, very bad resonator. Why? Because it actually leaks out too much light. I'm going to talk about photon lifetime. Basically, a good resonator is a resonator that traps light for a very good time. So this actually is a lousy resonator, but this is a winner. Every time I write a proposal about WGMs, this is what I want to put there, because of course it's very shiny, right? But this is not, so this is a failed resonator, but actually for pedagogical purposes, actually it's an excellent one. So when you have a good one, so not this one, when you have a good resonator, you can actually trap light for like 1 microsecond. It looks like it's not a lot of time, but actually it is a huge amount of time. Typically, if you have the laser pointer, for example, with a semiconductor laser, the photon lifetime in the semiconductor laser cavity is going to be like 1 picosecond, right? So here you can trap light for 1 million times longer. In 1 microsecond, light makes 300 meters in vacuum, 200 meters in this media. So basically, in these little resonators, you can actually trap light for quite a time. The number of reflections we have here is like 10,000 round trips. So basically, light is going to make like a little hamster. It's going to do something like 10,000 round trips before being annihilated. And annihilation here is either absorption within the material, outcoupling which is what we desire, actually, if the photons get out this way, where it makes us happier, or just radiation leaking out through the cavity. And this is how actually we can see this light, right? And here you have something like 40,000 reflections per round trip. So in the previous picture, here we have, I don't know, something like, I don't know, 8 reflections, right? But here, basically, we have something like 40,000 reflections to perform a round trip. So the photons bounce a lot on the edge. And basically, the link between, once again, these type of resonators and I'm coming to you in just a second. This type of resonators and clocks is just that basically when you have a typical clock in your hanging on your wall, you have the hands of the clock that gives you time. Here, basically, we are going to use the photons basically to give us the time. But of course, it's going to be a much faster clock. And here, of course, you can understand that you need to control this cavity very, very accurately, because just temperature fluctuations make this cavity bigger or smaller. It means that the photons take more or less time. So all the uncertainty of your clocks are going to depend on how well you can control this cavity. Yes, sir.
Yeah. So when you say reflections here, it is in an approximate like ray optics picture of like a,
That's absolutely true. That's yeah.
When you actually solve Maxwell's equations, it's more of a circular mode.
I absolutely agree. And actually, that's the next slide, but you're totally correct. So I'll just repeat this question. It was like, when I talk about total internal reflection, this is a ray optics approximation. But in reality, if you really want to understand what's going on, you need to solve Maxwell's equations for the cavity. You're totally correct.
How do you quantify how many reflections?
That's very good. That actually is the next slide. So you're really in it. But this is a great question, because actually the ray optics interpretation is very intuitive, but once you really dig into the topic, you of course have to go electromagnetic, right? So that's a great question. So here we are. So this is the ray optics interpretation, and as our colleague here said rightfully, when you want to study this system, in reality, what you have to do is you need to solve Maxwell's equations and with the proper boundary conditions, right? And now you see that instead of having this ray optics interpretation, now you actually have modes inside the resonators, and you have eigenmodes and you have eigenfrequencies. And now you see how we're falling back to our beloved comps. So basically, when you solve Maxwell's equations tell you, look, you will have some particular modes here, so eigenmodes. These modes will have a particular frequency, and these eigenfrequencies are going to be distributed almost evenly in the frequency domain. So now, where does, and that was actually the meaning of the question, what is the meaning now of the number of reflection that we have here? Basically, when you solve these equations, of course, you will have eigennumbers that will be, that will come from solving the eigen equations. And each mode here, in the simplest case, is going to be labeled by a single eigennumber integer L. So for example, here we have 1, 2, 3, 4, 5, 6, 7, 8 reflections. So this mode, for example, could be the mode L equal 8. The following mode is going to be the mode L equal 9, meaning that that is a mode that will correspond to 9 reflections to perform a round trip. And this will be in mode L equal 10, L equal 11, etc. So now you can label the modes by an integer number, and the physical meaning will be in the ray optics approximation that will correspond to the number of times you will have to bounce through the inner periphery to perform a round trip, right? Good.
Yeah. Is it right to think about these as longitudinal modes?
Absolutely. So the question is, are these longitudinal modes? Yes, they are. So basically, here you have 3 eigennumbers, one for the longitudinal direction, one for the polar, and one for the radial. But in the simplest case, you can also fix what we call a mode family. You can disregard the other eigennumbers, but those that are important for what we want to do, because we want to do comp stuff, is the longitudinal, basically the longitudinal eigennumber. It's exactly that. Do you have another question? No? Okay. So
yes.
Yes, please go ahead.
Right. So in this picture, it seems like you're inviting us to think of the mode number for the wave interpretation as being the number of half waves that fit going around the.
That's correct.
So, if I were to compare the ray optics approach, that is the number of reflections, to the number of half waves, are they the same, or do they have anything to do with each other?
I think they're the same. Of course, it is an analogy, so it has all the benefits and limits of an analogy. But within the reasonable bounds of the analogy, it is the same thing. So basically, the image here, the L here, is exactly as the N that I showed, I think, in slide 2 or 3 with the string, the vibrating string. This is the same eigennumber.
Okay, thanks.
You're welcome. Okay, so now you've seen with this huge detour, now you see why we're interested in comms and why this interest in comms now leads us to have interest in these WGEM resonators, right? Good. So something that is very important, that is because every time people talk about these resonators, they say high Q resonator, ultra high Q resonator. What does that mean? The Q factor we've all learned is just the ratio between if you have a bandpass filter, the Q factor is just a dimensionless number. That is the ratio between the center frequency and the bandwidth. Okay, so basically, when we say ultra high Q factor, we mean either we have narrow line widths, either we have ultra low losses, or long photon lifetime, because basically the lifetime, how much time a photon remains in a particular resonance, is just going to be equal to the inverse of the resonance line width, right? So we use these expressions interchangeably. But something that is very important is we need ultra high Q resonators, because actually we want the photons to remain in the resonator for a long time, so that we can give them the time to interact with other photons. This is where, as you know very well in nonlinear quantum optics, the quantum effects come from nonlinear interactions. So to increase the probability of these nonlinear interactions, we actually need to make sure that the photons have enough time to mingle. So here, for example, as I said, once again, I just repeat, the green photons underwent 40,000 reflections to perform a round trip, and the photon lifetimes were about a microsecond. Okay. So something very important that you get when you use, for example, these disks, is that the fields are confined basically in a torus. So here, this is a rim, this is a side view. So here it's like you're looking at this disk from the rim. So this basically is how confined the fields are. And basically, we know that the nonlinear interactions, because this is what we want to enhance, the nonlinear interactions are going to be enhanced by, first of all, the strong confinement of the light inside this torus, and by the long photon lifetime. So this is why we want low losses. And now we have two cases here. The first case is when we have a linear cavity. When you have a linear cavity, the photons do not interact, and each mode is independent from the others. So you have no mode coupling. It means that you take a WGM resonator, you pump it with a green laser, all these photons will remain green for the rest of their life, which is actually very short. Long for us, but I'm sure that it would like to live longer. Good. However, if the cavity is nonlinear, then the photons now can interact via the light-matter interactions in the medium. And this is how you can, for example, pump the cavity with a green laser, and now these photons will hop from green to other colors. And this is actually how you obtain a comp. So in a nutshell, this is what we want to do. We want to take a little resonator, very low loss, pump it with a single laser that has one color, and count on the nonlinearity to give us for free the comp. Okay, so this is basically what we want to do. So now we can go to quantum microcomps. Now you have an idea of our setup. We have a resonator. We want this resonator to be very low loss. We want to pump it with one frequency, and we hope that the nonlinearity will help us to actually excite the other modes. Yes, please go ahead.
This picture where you have one leave the mode about the sound on the photon. So has been proven or argued that this kind of spherical perfect geometry is the optimal one for this, or there is some better geometry?
That's a good question. Actually, today the problem if you have a spherical resonator is that generally the polar
it's very warm in here.
Sorry, the polar confinement is not very good. So generally, when you have a disk, you don't want the spherical configuration. You want something where the edges here are going to be a little bit slanted, because basically you want a stronger confinement here. The nonlinearity is enhanced by a smaller mode volume. So
I'm thinking that if you have something with imperfections, they may help localize things. So if you have people talk about making it imperfect, just for the sake of localizing it a little better, or there's.
I would say in this setting, imperfection. So the question is, do we want imperfections here? It depends. If these are controlled imperfections, then it could be useful, like a grating to outcouple the light. That could be good. But if these are random imperfections, the problem that you'll have is basically you have now a bad resonator like this. Because this here, you see, all the light leaks out is because the rim here is not sufficiently smooth. To have very high Q factors here, you need a rim that has a smoothness that is down to a few nanometers, right? So if the surface roughness is too high, then when the photons bounce, well, they escape basically, and you don't want that. So generally, we want here to avoid imperfections as much as we can at the rim, but also inside the material.
Is surface roughness always the main thing that limits the Q of these resonators, or does loss in the material play a role when you get the surface good enough?
That's a great question. For the crystalline resonators, the surface roughness is always going to be the limiting factor. So the best Q factors you have here are 10 to the 9, 10 to the 10. If we had the limit, if the losses were only intrinsic, so the bulk losses, we'll be able to go up to 10 to the 14.
Yeah.
But unfortunately, we're limited to 10 to the 9, 10 to the 10 because of this surface roughness losses. So that's our limiting factor here for the crystalline parts.
And what about the bandwidth? Because of course, low loss in a material usually is restricted to a certain bandwidth.
That's true. It depends now on the span of your comb, right? For example, here, if you have a comb here that is spanning, I don't know, a few nanometers, honestly, you're well within the quote-unquote transparency window, right? But if you want to have octave spanning combs, which is something that is very useful for metrological applications, then of course you need to look at the fact that the losses are dependent on wavelength, and then it becomes important.
Yeah. Okay.
Yeah, sure.
What about the race rate? Because instead of having like perfect resonators, people try to use the race rate.
Definitely. That actually, a lot of people are working along that line. The advantage there is actually sometimes they go even beyond a racetrack. Basically, they do like this RFID patches where it goes and it's involved like that because they want basically to have a very long perimeter in a small footprint. So you can do that. The problem sometimes is just the bending losses. When you ask these photons to make like these U-turns, they generally have the tendency to radiate away, right? So you gain by having a smaller footprint, a larger perimeter, which means that the FSR, so the modes are closer, and in some applications you want the modes to be close enough. So that's the plus. The minus is that the more windings you have, then your bending losses become very, very large.
Just follow up sort of on Victor's question. Like if I think of this small ring as like sort of a short waveguide, like could I introduce, what Victor was saying, basically sort of clever modulations to confine the light, not only like along the ring, but also like along the ring. So
you can definitely do that. And then have some kind of photonic crystal, right? Yeah, actually some people start to work on that. I've been starting to work on that. Definitely you can do that. But once again, once you bring these corrugations, there are more losses. But now you bring in new trade-off. There are new functionalities that are enabled like that. That's true. So here I would like first to quickly introduce, now that we can talk about quantum microcomps, I would like to introduce first of all electro-optic comps, right? So most people here possibly are familiar with what an intensity modulator is. It's a very cool device. What it does is that you at the input you have a constant power. So this is a laser beam. So in the Fourier domain, that's a single mode. And then you basically here have a radio frequency signal, which is lower frequency. So this typically is going to be, 200 terahertz. This is 10 gigahertz, 1 gigahertz, something like that. And what it does is that at the output, it modulates your amplitude. So this is a very common, widespread device used in optical communications, because basically this is how, at least at the beginning, optical communications operated. So here basically you can have your binary stream 0, 1, 0, 0, 0, 1, whatever, and here you have on off on off on off, and this is what you learn from the fiber, right? Good. The nice thing here is that the fact that now you have here an intensity modulation means that when you go to the Fourier spectrum, now you have some side modes here. So you can see the difference between both spectra here. So now the interesting thing is that if instead of having an intensity modulator, you have a phase modulator. So at the input, same thing. You have here constant power. You have your radio frequency signal. At the output, this is what you have. The power remains constant, but now your phase or your frequency is modulated. In the frequency domain, you still have a spectrum that is a comb. So this is a frequency comb. This is called an electro-optical frequency comb. And the nice thing here is that you can control the spectral distance between the comb with this frequency, because this distance between modes here is just this omega. So here, these are perfectly controllable comps. But the interesting thing is this, is because the power is constant, actually the amplitude of each of these modes here is going to be proportional to a Bessel function. And we have this very nice property of Bessel functions. It's equivalent to cosine squared plus sine squared is equal to 1 for Bessel functions. And basically, you can use now these equality for quantum purposes, as I'm going to show in the next slide. So basically, what happens now if you send just one photon inside this phase modulator? Okay. Now, if you send just one photon inside this phase modulator, what happens now is that it can, and you can call this photon 0, so it has the frequency of the laser. It can hop onto any of the adjacent modes with a probability that is going to be proportional to J square of S. This S is basically proportional to the intensity of the modulation, right? And basically here you have what we call a frequency beam splitter. Because what happens now is that you inject a photon here, and it will have a certain probability to come here, or here, or here, etc. And because we have this very nice Bessel function equality, this basically now just means that the sum of the probability is equal to 1. So you send your photon in, and with probability 1 is going to end somewhere. Okay, good. And now this is very interesting because when, for example, you do experiments with polarization in photons, you have the polarization beam splitters that are, for example, going to be 50-50. So you have a photon that arrives somewhere and 50% chance to go there or there. But now what you have is you have a photon that arrives, a photon that arrives here, and it has this probability weighted by these squares of Bessel functions to hop onto a different frequency. So this is why we call this a frequency beam splitter. The nice thing now is that unlike with polarization where you only have 2 degrees of freedom, here you can have up to 9, 11, so it's more. So here I will go yes, okay. So S here is basically this thing here. I didn't want it to. So basically, it's going to be proportional to the voltage that you put in here, and the V pi is basically an intrinsic characteristic of this phase modulator. So it's a dimensionless parameter that is in the order of 1.
But in principle, Bessel function has 0. You can pick it so that it doesn't feel.
Oh, definitely. That's absolutely true. Like you can see it here, you're totally correct. So there is a probability that the photon just remains at the same frequency. The opposite in which.
Index 0.
Oh, yes. Oh, definitely. Oh, yeah, of course. Yeah, sorry. That's a great point. The thing is now you have to be careful about how, of course, what you want your S to be. But once again, it's totally controllable, okay? This is basically a data sheet characteristic of this modulator. But this Vmax here, you can definitely control it. But yes, you need to find the S such that you have the distribution that you want. If you choose the wrong S, at some point you can nullify the probability for it to go in certain bands. That's absolutely correct.
I'm sorry, I was just thinking it would be kind of curious to see zero probability of it being in the same state.
I think that is definitely possible. So basically what you were saying is I now understand your question. Basically, can you choose S such that you nullify G0 of S is equal to 0, right? It's absolutely possible. And actually, this is why these electro-optical comps are so interesting, is because you actually have a lot of control on the quantum interference that are happening. So here I'm going to go relatively quickly here because I don't want to get into the details of the experiment. But basically here, this is an experiment that was made. It's called frequency path interferometry. So you have here a source, SPDC source. You split them, so you have here some kind of rainbow. So this is generally how we image comps. Say, hey, we have a lot of colors. We pass them through a phase modulator. So the phase modulator basically now creates the indistinguishable paths in the frequency domain. And at some point we do, of course, the correlation detection. And normally we should be able to see quantum interference. And if you want more details, this was published in this paper here a few years ago. So basically, I'm also not going to stay long here in the model, but basically this is how you describe the quantum state. So you have a continuum here in the frequency space. And basically what you try to do is, you know what is the quantum state at the beginning, and you want to use the frequency state at the end of both arms A and B to see if you have some kind of a quantum interference. I jumped to the main result because I think that this is what is the most important. So here, you have basically, of course, when you have interference, you have a difference of phase, and you want to see how your system behaves as function of the difference of phase. When you have an interference with plane waves, of course, you have a cosine square profile, right? But when you have an interference with this type of system, actually, your interference pattern is going to be some kind of Bessel function square. So this is why here the interference pattern doesn't look as a cosine square, but instead it looks like a Bessel square. So if you have no dispersion in the fiber, so basically in this study, you wanted to understand what's the effect of dispersion, the imperfection of the fiber when you want to basically transport a quantum state over a long distance. So if you have here the perfect situation where you have GVD is group velocity dispersion, so that's dispersion in the fiber. If you have no dispersion and you have perfect filter, so you can pick the frequencies that you want perfectly, you see that the interference pattern, so basically this is here you have the distance in kilometers. Here, of course, the phase difference. You see that the interference pattern does not change. So here, what is very bright here is this peak. And of course, here, the one here and the one here are these two little peaks, right? So here you have an interference pattern that does not change. It means that you have a quantum state and you're able to transport it over 60, 80 kilometers with no alteration, which is, of course, ideal, right? But this is when you have the perfect situation. So what happens when now you have dispersion in the fiber? Dispersion in the optical fiber means that different colors travel at different velocities. If you send blue and if you send red, the blue photons and the red photons don't travel at the same velocity. Then if you do that, what happens is that you will have some type of oscillation in the interference pattern, right? And now the situation that we have in real life is that we have dispersion and we have non-perfect filters. You see that basically your interference visibility degrades. So here, for example, after 4 kilometers, you see we are here at the red curve. So you see that the visibility decreases. And after 60 kilometers, you see that we are at the dotted blue. The visibility is, the dotted blue is 4 kilometers and the dashed is the 60 kilometers. And you see that the visibility goes down. So this is what numerical simulations tell us. Yes.
Sir, maybe that's because you went too quickly to the previous slides. Actually, I have no idea what's going on now. So what kind of light did you inject? Yeah,
That's true.
So there's a state modulator. Is that used?
No, that's a great question. That's a good question. No problem. Here, the phase modulators are here. So at some point, when you want to do quantum interference, you need to create these indistinguishable paths, right?
What's the source? So
the source here is basically SPDC. So basically, we have
a theory slide, right?
Yes, exactly. Yes, it's explained here.
Right, okay. Cool. Okay.
Yeah. So here we have BPLN popped at 70-75, creates spontaneous parametric down conversion continuum, and characterized by this F of omega.
Okay, so that's the source, and then it goes
into the phase modulators in two different arms.
That splits it into like more.
That's true. Is exactly. It splits into more frequencies. Here.
And then you send it into your resonator.
No. At this point, we're not using resonators. At this point,
resonator.
no. At this point, no. These are electro-optical comps. So I wanted to explain the contrast. Make sense? Okay. Sorry. At this point, I don't want to abuse your time. So now I'm like, okay, I need to be able to move a little bit faster. But it's because I don't want to go overboard way too much.
Is there nonlinearity now somewhere?
Yes, but here, yes, if you will, but the nonlinearity will be in the source, basically.
That's easy. Okay, so everything else is dimensional.
Yes, that's true.
Now, when I look at this diagram, it doesn't look very quantum. I mean, is there some like Hungo-Mandel thing going on somewhere?
Yes, if you will. Basically, this is a quantum interferometry experiment. So here, basically, once you send out the photons here, basically you have some. You can call that HOM interferometry, but in the frequency domain, if you will. That's basically what's happening. Yes, please.
You use the same frequency with the classical light. Source.
Mm-hmm.
You get the disappearance pattern.
Yes. Yes, it would. Yes, it would. It will not be the same. So here, basically, I know that like it is exactly the same as like when you look at classical Young's experiments, right? You can be okay if you do the experiments at and you send single photons, and when you do the experiment with classical light, someone can say, okay, look, with the classical light we see an interference pattern, right? So when you see that with single photons, why is this a quantum effect? It's pretty much the same thing. Not convinced?
The result with the classical light will be the same as the single photon detection, because accumulated on.
Exactly. I mean, yeah. So this is basically you can see here we have a single photon counting here. So it is exactly as if when you do once again the Young's experiment, if you shoot photons one by one and you see interference, this is a quantum effect, right? If you shine classical light, you will also see an interference, right? But that is a classical effect. So it's exactly the same thing here. We see an interference pattern, but when photons arrive at the photon counting level, instead of like when they're just like bright light. Yes.
Can I ask a follow-up? So just to make sure I understand, like if I were to send classical light and do homodynamic detection and look at the variances, is a statement that like I wouldn't be able to detect this from velocity dispersion like via that homodynamic detection. I guess the confusion is that the thing that we're detecting seems to be a classical effect. Like of course this experiment is like very quantum. So it's a statement that like doing this interferometry would be like we provide an advantage in detecting that effect, or what is it?
No, basically, I understand your question. Basically, the reason we did with this experiment was the following. If you do the experiments in the lab with like, 1 meter patch of fiber, you see quantum interference, right? Good. The question is, if you propagate this state in optical fiber after 60 kilometers, are you still going to see quantum interference? How does propagation along 60 kilometers of optical fiber deteriorates the quantum interferometry? That's actually what the experiment is about. Make sense? So
if I could go back to, if you could go back to that previous
sure,
slide,
sure.
just to make sure. So the source is a parametric down conversion, so it produces entangled photons. Is the splitter sending the signal on one arm and the idler on the other, or is it just a regular beam splitter?
It's a regular beam splitter.
Okay, so both signal and idler are on both arms.
Correct.
Okay.
Yeah. And once again, just to show you the big picture here. Of course, I want to talk about quantum comms, but I wanted to show you an experiments that we do with other types of comms. Because at the end of the day, when you have a comm, like it doesn't matter where the comm is coming from, right? So here, this is something that we did with electro-optical comms, and soon enough, I'm going to show you what we do with quantum Kerr comms. Once again, the advantage of electro-optical comms is they are much more controllable. You can control the distance between them, et cetera, right? While for a quantum comm, it's a little bit more difficult. You just pump the resonator, and then it's a prayer, it's a Hail Mary about, okay, what's going to happen? You don't have as much control as with electro-optical comms. And at the end, I'm going to show the pros and cons of each method. So here, the last, little point that we wanted to eliminate, a loophole basically, is the following. Because we have a source here and we have two arms, there is a patch of fiber where the photons propagate in the exact same loop, and when they propagate in different fibers. And for reviewers, this makes generally a difference. When you generally submit these papers, if you propagate, you say, okay, I'm doing a quantum non-locality experiment. If at some point your photons propagate in the same fiber, they're like, wait a minute, everything is local. These photons were together all the time, right? So at some point, we wanted to understand, does it make a difference if the photons, all of them propagate in the same fiber, or if they really have to propagate in different patches of fiber to prove that we actually have these non-local quantum interference effects. So this is what we call the co-propagation or split propagation dilemma. And we basically made the experiment in both configurations. And these are the experimental results. So basically, regardless, I'll make it short, regardless of if the patches were short or long, like 30 kilometers, doesn't matter if it's split propagation or co-propagation, we observe exactly the same quantum interference effects. So basically, this is really genuinely a non-local quantum interference phenomenon. And it doesn't matter if you make this photon propagate in the same patch of fiber or if they propagate in different patches of fiber. Okay. And what you see here, the lines are the results of the numerical simulations, and the symbols are, of course, the results of the experiments. Good. So now that I showed you what you can do with electro-optical comms, so when you take these modulators and you get comms with them, let's see what you can do with quantum Kerr comms. So with quantum Kerr comms, basically this is how it works in a nutshell. The quantum nonlinearity, the Kerr nonlinearity is a nonlinearity where it's called four-wave mixing. It's a very telling name. So you have two input photons here, alpha and mu, they interact, and you have two output photons, beta and eta, right? Good. So to have this interaction, of course, you need to have conservation of energy. So basically, the sum of the frequencies before and after have to be the same. And you need to have conservation of angular momentum, because now this L eigennumber actually can be interpreted from the quantum point of view as the angular momentum of the photon, and it needs to be conserved. So basically now what happens is that when you have your cavity, your WGM resonator, and you pump it with a green laser, now you have two photons. One can be up converted like this, and the other one down converted. You can have this reaction. You can have that one. All of them actually obey this very simple photonic reaction. You have two pump photons. One is up converted by n times the FSR, and the other one has to be down converted by n times the FSR. And as we know in quantum physics, when multiple things can happen, well, they actually do happen with particular probability. So basically, your quantum state now looks like this. So now this state here, this is called spontaneous four-wave mixing, because this process here is spontaneous, exactly like spontaneous emission in a laser, now creates a state that is this state here, which is a quantum superposition of both photons, sometimes they're called biphotons, being here, or being here, or being here, etc. And because we have several tens of modes, basically we have created an entangled state over easily 10, 50, sometimes 100 modes. So instead of having a qubit, we have actually a qubit. This is the main interest of working with quantum microcomps. Now, there's no free lunch. You don't have that much controllability on the states here. Like the colleague was suggesting, for example, with electro-optical comms, you can play with the S and have the interference patterns that you want. Here you can't, but here you have a much larger quantum superposition. So this is then how it works. And generally, with this type of systems, instead of working with crystalline resonators, it's sometimes preferable to work with integrated resonators. The Q factor is lower, so the losses are higher, but you have much more controllability on what happens, right? And then what happens is that here you pump it with a particular wavelength, and then your photons are basically distributed in this fountain-like fashion and create basically these entangled states here that can be up to like 100 dimensional. And here, basically, yes, please.
So, so you write it as if there are only like two photons. That's what that wave function is.
Correct.
I assume, like, are you pumping hard enough?
That's the thing. That's true. If you pump hard enough, then the quantum state becomes much more complicated, because now this photon here might, if it's strong enough, it might create its own fountain, right? And then you have a cascaded thing that's now second order.
Are you pump it, or you pump it always weak enough that you guys?
Oh, that's a great point. Always weak enough, such that you can say, okay, I only consider the four-wave mixing from this main pump, and I disregard the potential four-wave mixing from the adjacent side modes. That's a great point.
But even if I am within that approximation, I can still like kind of repeat that same process from the pump out like twice. Like other say, are these two photon modes sort of doubly populated? Like, you see what I'm saying? Like if I repeat the same thing twice, I mean, I'll get 4 photons. So they're all kind of that.
Maybe something here that this is a continuous wave pump. So here, this is just feeding photons continuously. Does that answer your question?
I mean, I should be creating a squeeze state there, not just 2 photons. Like I should be creating 2 photons, 4 photons, 6 photons, 8 photons.
Yes, that's true. Yeah, when you make the expansion, but if you pump low enough, you can neglect these.
So you've been pumping so low that at any time I have basically only 2 photons.
That's true. That's true. That's true. That's exactly that. And I see. Yeah, because when you do this, then you have that expansion. Yes, yeah. So here the KK, and I will explain that these are frequency bin states, and I will say a few words about that. So I showed this picture at the beginning, and I did block Rogue Lauber because I was talking about comms, but now it needs to appear because now we're talking about quantum stuff, right? And as everybody knows, he's the one that co-developed with Sudarshan, co-developed the tools of like, you know, coherent states and annihilation operators and like, you know, the second quantification of electromagnetic fields. And interesting, so now I have to block the others. And the funny thing is, I'm sure that in 2005, when they awarded the prize, they were like, okay, this is the year where we're going to honor these colleagues. I don't think that they thought that quantum optical frequency comms was a thing back then, but now it's becoming a thing, and it's kind of like an interesting coincidence that now the contributions of all these colleagues are merging into a new field. Now, real quick, how do we analyze mathematically these quantum Kerr comms? So here you have the equations for the classical comms. So basically, this is an equation that says in the mode L, you have losses. This is the tuning. This is dispersion. That's the pump. This is the nonlinearity. So you see here the forward mixing. So these three modes here interact with this forward one. We'll not get into the details of all of that. It's not that important. And basically, the way you obtain quantum equations from this is by a process that is called canonical quantization, where basically you replace the slowly varying amplitudes here with annihilation operators, the conjugate with creation operators, and something else that you have to do is to add vacuum fluctuation terms here. And of course, you know, remember that these fellows here don't commute, which when you do the calculations is always very, very funny because of course we're used to commute everything, right? But when you do the calculations with this, you have to be very, very careful. Like for example, a very simple thing. For forward mixing here, for aesthetical reasons, we always put this star here in the middle. But when you do the quantization, you need to be sure that you have some normal ordering. So now you need to put the creation operators at the front. These are just details. So here, of course, when you pump hard enough and now your states are oscillating, then you can have squeezing. For the interest of time, I will skip that real quick and get to the most important part of the quantum microcom modeling. So basically, when you're under a threshold, this is what happens. Because you can only consider the pump mode and the adjacent modes, basically you can simplify the equations like this. And these are basically what are your quantum Kerr spectra going to look like. So here, you see this is the mode number here. Okay, so this is where you have the pump. We filter it out, and basically it tells you basically that this is how your adjacent modes are going to be populated, right? And here the A, B, C, D. This is just various conditions, changing sigma, changing the laser frequency or whatever. So when you zoom inside these modes, you can see that actually they have structure. For example, here you can take one of these modes here. They're tightly packed, so you cannot see. But if you take one mode and you zoom it out, they actually have a width, right? And they can have particular features. So the modes that you see in green here, they are modes that only have one peak, and the modes that you see in red here are modes that have two peaks, right? And basically, when you pump these resonators, all these modes are filled. So actually you have a bunch of photons, and this is a continuum in terms of frequency. Yes, please.
So if you were in the strongly strong pumping, you have the frequency column and it's classical.
Mm-hmm.
If you're in the weak complement, Alexei was asking, you create this photon pair.
Mm-hmm.
Now you're in between these limits. Or no, you're.
I'm still at the limit where I pump so low that I only have the fluorescence spontaneous forward mixing. So this is weak pumping.
But then you have a phone.
Yes, because basically that's a great point. I have it come because basically this is the fluorescence noise basically here. Exactly like when you see the fluorescence spectra of a laser, right? A laser on the threshold. If you look at an OSA, you will see. You will have like in the spectrum, you'll see basically the fluorescence photons, right? Basically, this is fluorescence, but it is fluorescence from the spontaneous forward mixing. Because regardless, your pump is low, so it's just feeding these photons.
As like an nonlinear crystal,
Mhm.
that over there I have a continuous number of modes in K,
Yes.
K idler and K signal. But now your resonator has filtered a lot of them. So I have a discrete set of.
That's exactly that. So that's exactly that. So basically here, it's a crenellated spectrum. So it's actually a continuous spectrum that is carved out by the resonances of the resonator. That's actually what it is. So now, how do you characterize this quantum state? Very quickly, as you know very well, Glauber and Sudarshan, they developed the coherent states and Fock states by other people. But here you have, honestly, you have thousands of photons. So you cannot have a quantum description in terms of, like, for example, Fock states, because there are way too many photons. So here we use something that we call the frequency bin representation, which basically is to say, okay, we are going to label photons by which mode where they land. If they land, for example, in the modes -1 and 1, then this is how we're going to label the photons. And when we do that, basically, this is basically the quantum representation of these cats. We are able to calculate the probability amplitudes, and from there we can define the quantum state as this quantum superposition. So, long story short, here we are able mathematically to give a complete description of the quantum state here, because we are able to mathematically define the frequency bins and mathematically calculate the amplitude. And of course, the sum of the square amplitudes are equal to 1. C, K here is real valued, so this is a Schmidt decomposition. And here, for example, you see the fluorescence spectra. So this comes to the question of Mohammed. So here we have a resonator that is less packed, and you see basically this is the fluorescence spectra, and the dots here basically are the probability on 2 photons emitted that they land in a particular spot. And this is where I just need 2 minutes to finish. Now, the interesting part is this: when you describe a system like this, basically you make the implicit assumption that you have a pure state. But here, we do not have a pure state because you have a lossy system. A lossy system cannot be in a pure quantum state. When you have a quantum state, it's because you consider that you have an isolated system, right? Good. But when you have an open system, it cannot be closed, so it's lossy, it's interacting with its environment, and then you cannot describe it with a ket. You need to use something else. So here, very short review. As you know, closed quantum systems are isolated. You can describe them as pure state or linear superposition of eigenstates, and basically they tell you all what you can know about the system. But when you have an open quantum system, then basically you need to use the formalism of mixed states, right? You cannot describe the system with kets. And just a little bit of math, but I'm sure that almost everybody here is familiar with that. For a pure state, basically, this is how you describe the state, and this is how you build the density matrix. But for a mixed state, basically, you need to have a linear superposition of projectors that are weighted by probabilities for each eigenstate. How you disambiguate them is that the purity of a pure state is going to be equal to 1. The entropy is going to be equal to 0. While for a mixed state, the purity is going to be smaller than 1, and the entropy is going to be strictly positive. So how do we model our lossy system? Well, what we do is we use this very old technique that is called purification. We say, okay, the system is lossy, but if we enclose the environment, well, it is a closed system, right? And then we basically now create this ket here where A is the system, B is the environment. So basically here the losses is this eta and 1 minus eta split. So the efficiency here is eta. It means that the photons have a probability eta to be outcoupled here, and a probability 1 minus eta to be beam splitted to the environment. So basically we say, okay, this full square here is a closed system. So we can write this as a ket. And then we just write this superposition like this. So basically here we have the case where the idler and signal are in the system, where one system is in the system, the other photon is lost, the opposite direction, and the case where both photons are lost. And this is, of course, a pure state, a fictitious pure state. And now we describe our system by tracing out the environment. So this is the total density operator. We trace out B. This is standard technique. And now you get the density operator for our quantum system. And here, this term here has to go away, because basically here you're saying that both photons are lost to the environment. So it is experimentally irrelevant. You randomize, and then you get the density operator for your quantum system. Good. So that is the main result. Once you have that, the nice thing about having the density operator is that you can calculate metrics for quantumness, like the fidelity. You can calculate the purity. You can calculate the entropy. The nice thing, once again, once you have the density operator, is that now you can mathematically determine how pure your quantum states are, how close they are from pure, depending on the parameters of the system. So that's the big picture. When your system is pure, you can describe it as a ket. So this is the lossless configuration. But in the real world, lossy configuration, this is where you have to go. And here we are capable of calculating all these coefficients. So here, basically, this is just a comparison between electro-optical comms and Kerr comms. I'll not get into the details of that. I think that we had the opportunity to discuss all of them. But basically, you can see here, Kerr comms, everything is green, means that it provides a lot of pros. But the red here is the highest difficulty of implementation. But when, for example, you do quantum experiment with polarization, everything is rather straightforward, and it has actually the lowest difficulty, but you don't have a lot of dimensionality. So this is the last slide. I always say the research that we do, we always have scientific and technological challenges. From the science point of view, we still have a lot of things to understand. From the technological point of view, everything is about like optimization, robustness, swap, etc. So I'd like to thank the Department of Energy. They are the ones that are funding most of this research. My French colleagues from CNRS, they are the ones that mainly did the experiments that I showed about the electro-optical comms. And thank you very, very much for your very kind of help. First of all, I'm sorry at the end I rushed a little bit, because the thing that generally when I'm in the audience, the thing that I don't like are speakers that go 30 minutes overboard. I don't like that. So when I'm a speaker, I try to be very respectful of your time.
Well, as the audience, you again prevented the speaker, all the way through.
It's all right. 12:03. It's not too bad.
Time one question. If it's short, not Bill. Already. One question, and we'll go to lunch, and the speaker will be around. We'll have one last question.
Yes, please.
So can you say a little bit more about kind of this more interesting regime where you kind of pump it strongly and like these extra photons you create and they split up as well? There's got to be interesting to anybody who's problem like this.
It is actually more than interesting. It's fascinating, but also very, very hard. Basically, the question is about when here you pump hard enough such that these modes here as kind of like secondary pumps, right? And then you have this cascaded regime. I'm personally very interested with that, but it is very, very hard, because now you have like nested orders of but it is actually very passionate a lot, because there you have squeezing also that happens. It's basically, if you have a laser, what happens when you pump the laser at 99% of threshold? It's fascinating, right? Because in all the textbooks, they tell you what happens above threshold. Okay, you have lasing. They tell you what happens when you're way below threshold, you have fluorescence. But what you have at 99% is where all the magic happens. The criticality, and like, you have like fluorescent modes that are, it's fascinating, but also very, very hard. This is why it's not in textbooks.
Great. Thank you very much.
Thank you very much for making it.